Since people are exposed to radioactive substances, we use them, especially in medical fields, then or in veterinary as well. We need to monitor what our exposure is because it can be dangerous to tissue. We know it can destroy tissue. And the higher the energy, the more danger and the harder it is to protect yourself, the more requirements there are. And so we've got to be able to monitor that, and so we have to detect it first, and then we have to measure how much that you're being exposed to. And so the amount of radioactivity in a sample is measured by how many nuclei are decaying over time. Usually with the ones that we're going to be around, it's going to be disintegrations per second. And so what we use are curies. Okay, so a curie is 3.7 times 10 to the 10 disintegrations per second. And so a millicurie is 1,000. There are 1,000 millicuries in one curie, I should say. And then a microcurie, there are 1,000,000 in one curie. You also may see becquerels. Becquerels is 1 disintegration per second. So those are, the ones that are really fast. So since 1 becquerel is 1 disintegration per second, then there are 3.7 times 10 to the 10 becquerels in one curie. And so that's why you'll see becquerels or curies used, so you don't have to do all those big numbers. Radioactivity can't be detected by the senses. It's odorless, colorless, but it is very destructive. It will damage or kill especially rapidly dividing cells, and those are in bone marrow, skin, and your reproductive and intestinal systems. And if you notice, that's where cancer often is found. Cancer cells are dividing very rapidly as well, and so radiation can be a very effective treatment for cancer because it tends to attack those rapidly dividing cells. The problem with radiation treatment, though, is it attacks indiscriminately any cell that you're coming in contact with. And so it will kill the rapidly dividing cancer cells, but it will also kill the normal cells that are dividing. Food is irradiated, and a lot of things like spices are irradiated to kill microorganisms. They use radioactive methods that do not leave residual radioactivity. But so it's not going to be harmful to you. There is no residue to it after you eat it. That's mandatory for food. But it does give it a longer shelf life than other things, and so that's why things like spices and stuff like that are done. So we also, so the becquerel and the curie is like the amount of radiation you can detect in the environment or what a source is going to be giving off. But you also are interested in how much radiation is being absorbed by an organism, okay? Because that's really important, because you have to limit the amount of radiation you're absorbing, because over a certain amount you could be harmed. And remember, we have something called background radiation, and background radiation is the natural radiation that comes from the rocks and the minerals and the air and everywhere around us that does emit, and those things are typically not harmful. And so you have that as a background, and then you're going to add to every time you get an x-ray, or if you're working in a hospital. And so that's why a lot of times you wear a radiation badge if you're going to be around higher levels. So a RAD, okay, a RAD stands for radiation absorbed dose. Okay, and this is the amount of radiation absorbed by 1 gram. So the amount of radiation absorbed by 1 gram. A REM is radiation equivalent for man, and that's the amount of radiation that has the potential to damage tissue. 1 rem of any kind of radiation will produce the same type of damage because it's already factored in how high an energy that particular type of radiation is. So you can look at REMs across the board. It doesn't matter if it's emitting alpha or beta or gamma or whatever. The REMs are going to be already corrected for that type of exposure. Average radiation dose per year for a person is about 0.27 rem. Typically, as long as you're under 25 rems, you're not going to see any type of biological effect. If you get a single dose between 25 and 100 rem, you'll see a temporary decrease in your white blood cell count because it's going to kill some off. If you get a dose of more than 100 rem, you're going to get what's called radiation sickness, which is nausea, vomiting, fatigue. You can see hair loss, things like that. The LD50, which basically is that lethal dose that kills 50% of the population, is 500 rems for humans. Now, 500 rem is going to be intolerable, that is, kill off half of the people if they were exposed to that. 600 rem is fatal for everybody. So if you had a population exposed to a dose of 600 rem, everyone would die. So less than 25, you're okay. 500 and above, you're pretty much going to die. Between 100 and 500, you're going to have effects. Some people will die. It will depend on how strong your immune system is, how well you replace tissue, things like that, as to what those long-term effects are going to be. Now, having said all that scary stuff and being exposed and absorbing way too many REMs, we do use radioisotopes in medicine because they assist us in diagnosing things. And we use those that are not known, that they're going to be a low enough amount that they're not going to harm you, and the risk is higher than the risk is less than the benefit in this case. So radioisotopes can be injected or ingested to determine if you have a properly functioning organ, or it can also show a tumor. So like the technetium that we were talking about that gives off the gamma rays, you can evaluate gallbladder and bile ducts to see if you have leaks in there and so that you have internal bleeding. Thallium-201 is used in stress tests, and there's a lot of thallium used because we do a lot of stress tests because we have a lot of CAD, coronary artery disease. And so if you use a scan without doing, and so this is commonly called contrast, okay? So if you do a scan without doing contrast, it's very difficult to see. But if you use the contrast, then it's going to light up when they look at it, okay? And so whether it's an X-ray or it's some other type of machine. So for example, the gallbladder that I was talking about earlier, notice that if you have an issue, you can't see through a lot of the liver and the other things, but if you do a contrast, that's going to show up. And so you can see that you've got free flow in these areas, and then maybe not free flow in some of these areas. And so you could look at that and you could figure out where there was an issue. So and I'm not going to quiz you on these or anything, but it's just interesting to note the different ones that we use. The iodine 131 is used a lot, and the iodine 131 is used for your thyroid, hyperthyroidism, as I said earlier, destroying tumors. And they're literally poisoning that tissue by exposing it to radiation, and then you get rid of that iodine, within you know, several days, most of it's gone, and then, you know, over time, it's okay. But like when they use these in treatment, they have to collect the urine because the urine is going to be radioactive. And so it's very important, and the staff should be really well trained to do that. Phosphorus 32, leukemias, iridium 192. This has been used in breast cancer. Thallium, as I said, thallium is used a lot in cardiology to do that stress test and to make sure that the flow and there's not blockage and things. Xenon 133, believe it or not, for lung function because it's a gas. Technetium, the unstable type for bone scans, and also will do gallbladder and gastrointestinal bleeds. And so technetium is also one, and it's a pretty low half-life too, so it doesn't cause a lot of long-term issues. So a PET scan, or positron, get it? Positron emission tomography. PET scans use positrons that are emitted so that they can scan organs. And so they're very good for detecting soft tissue issues like tumors, coronary artery disease, hardening of the arteries, Alzheimer's, and progression of cancer. And so these PET scans can give us a way of monitoring what's going on without having to cut somebody or do some other type of invasive procedure. So that's why the benefit is there because it's non-invasive, and overall it's less straining on the system of the patient. And so when you have this one of these contrasts, as you can see, I'm showing you the basic anatomy with the kidneys and the bladder here. And so when you are seeing how you've got, is it healthy or is it unhealthy? Okay, so it's being maintained in the bladder because it goes into the urine and it's going to be excreted through the ureters into your bladder. And so in that bladder, you're going to see that accumulated, and it's going to be filtered and produced in these pretty healthy kidneys. Over here, though, what's going on? Okay, we've got a lot of bleed, it looks like. So we've got a lot of leaks, okay, coming out. And so in this case, that's going to show them, and they can actually pinpoint, somebody a lot better than I am at it, what exactly is going on with that. And so it's very helpful in contrast when you're trying to figure out what's going on with different things in soft tissue.